Hello and welcome. My name is Eric Gradner and I am a retired professor of mechanical engineering. In this video, I would like to present a 6-axis articulated robot that I've developed, along with a functional prototype of a completely new pose measurement concept. Let me begin with the motivation. Conventional industrial robots rely on internal joint sensors and kinematic models to estimate the position and orientation of the end effector. While this approach works reasonably well, it suffers from a fundamental limitation. The robot can only estimate its pose, and that estimate can drift whenever the payload changes. The joints heat up or structural components flex during operation, for instance, due to external loads. As a result, the true end effector position may differ from the calculated one, in some cases by several tenths of a millimeter, or even more depending on the specific robot. To overcome this, a measurement system was designed that determines the actual pose of the end effector directly, continuously, and independently of load and temperature. This system is built from high-resolution rotational encoders connected by carbon fiber rods, forming a parallel measurement structure that runs alongside the robot's conventional kinematics. See the title for the appropriate patent below. Each encoder axis is collinear with one of the robot's joint axes. This ensures that any rotation in a joint produces a clearly measurable and unambiguous rotation in the corresponding encoder. Because the rods are made of stiff, lightweight carbon fiber, the structure adds very little mass but offers a high thermal stability and minimal deformation. The result is a system that behaves almost like a second independent robot, one whose only purpose is to measure the true position of the end effector with exceptional accuracy. While the conventional actuators handle motion, the encoder rod assembly continuously reports the exact pose, allowing the controller to correct deviations in real time. Here on the prototype, you can see how the measurement rods connect the encoder modules across each joint. As the robot moves, the encoders track the rotations with a high resolution. The measurement data is fused with the robot's internal model, enabling the system to compensate for thermal expansion, bearing play, and structural bending. This means that even when the robot carries different loads or when its joints warm up during operation, the accuracy of the end effector pose remains stable. The prototype demonstrates that this approach is fully feasible. In practice, the robot maintains a highly consistent pose over long operating periods with far less drift than conventional systems. This opens the door to applications that require high precision without relying on external cameras, laser trackers, or complicated recalibration procedures. In addition, it is no longer necessary to design highly stiff robot arms and to calibrate these arms with high accuracy. Only the measurement system has to be highly accurate. The lower stiffness and weight of the robot arms makes the robot less dangerous to humans and has a lower power consumption. In this video, I have loaded the robot arm between the third and fourth servo of the robot with my fingers, and the resulting reaction of the servo on the third axis can be seen. The robot axes are actuated by a servo motor via cogged belt drive and a harmonic drive gearbox. Please excuse the quality of the electrical wiring. The robot is a prototype, and being a mechanical engineer, my electrical wiring skills are far from perfect. Thank you for joining me, and I hope you enjoy this look at an alternative way of achieving precise robot positioning.